Welcome back to Physics 191. I'm Gerard Blanchard. Last time we talked about rotational kinematics. That would be the angle that an object rotates through, the angular velocity with which it rotates. The angular acceleration tells us how quickly the angular velocity is changing. And we derived four rotational kinematic equations. For kinematic equations, very similar to the equations we have for x and y, vx and vy, ax and ay, except that they dealt with theta, our angle, omega, our rotational velocity, and alpha, our angular acceleration, or rotational acceleration. And before we move on, I would like to give you one more exercise in rotational kinematics to solidify these concepts. The question is, a turntable reaches an angular speed of 33.3 revolutions per minute in 2 seconds starting from rest. Assuming the angular acceleration is constant, how many revolutions does the turntable make during this time interval? Now, for those of you who might not be familiar with old-time record players, that's what a turntable is. It spins a record, a vinyl record, and one of the standard speeds was 33.3 revolutions per minute. Now remember to make a diagram of the initial and the final time, and you'll have to convert revolutions into radians. So I'll give you a minute or so to get started with that, and then we'll work on that. Okay, let's draw our turntable. Initially, we have our initial time, we'll call that 0. Our initial angle, theta initial, we can call that 0 as well. And omega initial, we are told is 0 radians per second because we're told that the turntable starts from rest. So time is 0 seconds, theta is 0 radians. Those we're free to choose, but omega initial equals 0 radians per second. We had to read out of the statement of the question. That's our initial situation. The turntable accelerates with some unknown angular acceleration. All we're told is that it's constant. And it ends up at a final state after it's rotated a few times, which is what we're trying to find out. We have a final time, a final angle, and a final angular velocity. The final time, we're told, is 2 seconds. The final angle is what we're looking for. The question asked for how many revolutions does the turntable make during this time interval. Revolutions is an angle. One revolution is 2 pi radians, so when it asks for revolutions, it's asking for an angle. So theta final is what we're being asked about. What is the final number of revolutions, or what is the final angle? Omega final, we're given as 33.3 revolutions per minute, and we'll have to convert that. We'll have to convert that to radians per second by multiplying by 2 pi radians per 1 revolution, and that'll take care of our revolutions, and by 1 minute is the same as 60. 1 minute is the same as 60 seconds, and that'll take care of our minutes. And so we can calculate that. that would be 33 times 2 times pi divided by 60, which gives us 3.45 or 46. No, actually, I'm sorry, I did that calculation incorrectly. That would be 33.3 times 2 times pi divided by 60. And that gives us 3.49 radians per second. So that is the final angular velocity. Now that we've gotten all the information that we can from the question statement, we have to identify this as a rotational kinematic situation. Rotational kinematic. And we do that by recognizing that we have a rotating object that changes its angular velocity over time. It changes its angular velocity over time. Now we have 4 rotational kinematic equations to choose from. We choose our rotational kinematic equation based on what we don't know and don't need to know. What we don't know is theta final. Now, we do need to know theta final because that's what we're being asked for. We don't know angular acceleration, and we don't need to know angular acceleration. We're not asked for that. So we must choose the equation that has theta final in it, but doesn't have alpha in it. And that equation is omega final plus omega initial divided by 2 is equal to theta final minus theta initial divided by t final minus t initial. This equation has everything we need in it and not what we don't need. So now, at this point, we have completely modeled the situation described in the question. Now it's just a matter of working it out. Omega final, we know, is 3.49 radians. Omega initial is 0 divided by 2 is equal to theta final, which is what we're looking for, minus theta initial, which is 0, divided by t final of 2 seconds, minus t initial of 0 seconds. And carrying that forward one step, we have 3.49 divided by 2, and then I'll multiply by 2 to get theta final by itself. So I'll multiply both sides by 2 is equal to theta final, and we can see that these 2's cancel out as well, and we have theta final is 3.49 radians. Now, the question asked us, how many revolutions does the turntable make? So we've gotten our answer in our basic units, but we'll have to convert back to revolutions by multiplying by 1 revolution per 2 pi radians. And so we have 3.49 divided by 2 divided by pi, and that tells us that the final angle is 0.555 revolutions. Now we'll talk about the relationship between rotational motion and linear motion. What I mean by that is if we have an object that rotates, then a point on that object will move a distance, a linear distance. So if I rotate this wheel through one complete revolution, 2 pi radians, then that black mark has actually moved a distance equal to the circumference of the wheel, or 2 pi times the radius of the wheel. If I move the wheel a fraction of that, such as from here to here, then the distance that the mark has moved is the arc length of that angle. So as the mark moves from here to here, it's covered an angle of 90 degrees, or pi by 2 radians, and the distance that it has moved is equal to pi over 2 times the radius, so the distance that the tape has moved. We can also talk about the velocity of the tape as it goes from here to here. If it covers that distance in a certain amount of time, then its linear velocity would be related to the angular velocity of the wheel. So if we let the wheel rotate, the linear velocity of the tape as it goes around is related to the angular velocity of the wheel. And finally, the linear, or what we're going to call tangential acceleration of the tape, is proportional to the angular acceleration of the wheel. Now, the reason why we call it tangential acceleration is if you consider, let me make the wheel rotate at a constant speed. If you consider, or as best as I can do it, if you consider that point going around the wheel, when the point is over here, it's moving up. When the tape gets over here, it's moving to the left. When it gets down here, it's moving down. And when it gets to here, it's moving to the right from your perspective. So the instantaneous velocity of the tape is always at a tangent to the wheel. So when the tape is over here, it's moving up. Over here, it's moving to the right. When it's here, it's moving down. Over here, it's moving to the right. So the velocity of the wheel, the velocity of the point on the wheel, the velocity of the tape is always tangential to the motion of the wheel. So this linear velocity that we're talking about we'll refer to as the tangential velocity of the tape, and its acceleration in that direction we'll refer to as the tangential acceleration, and that's going to be an important distinction very shortly. So if we look at the equations that relate linear motion to rotational motion, a point on an object that undergoes an angular displacement moves a distance equal to the arc length. So we would write, so you remember from trigonometry that the arc length is equal to the radius of the circle that you move in times the angle through which you move. Tangential speed is very similar. If you remember arc length is radius times angle, then all you have to do is substitute in the speed and the angular speed for distance and angle. So the equation for tangential speed is that the tangential velocity is equal to the radius times the angular velocity. And similarly, tangential acceleration is equal to the radius times the angular velocity. So what that means is that situations with arc length, tangential speed, and tangential acceleration are also rotational kinematic situations. Now there's another context in which this concept of linear speed, linear velocity, and angular velocity come up. And that would be, or a similar context, I should say. And that is when we have a rope wrapped around a drum. So now I have a string, and the string goes exactly one time around the wheel. The string is exactly one circumference of the wheel. And if I unwind the string from the wheel, you'll notice as I pull it off, as the string itself moves one circumference, the wheel goes through exactly one rotation. So the distance that the string moves, or that the distance that my fingers move at the end of the string, is equal to the radius of the wheel, or is equal to the circumference of the wheel, is equal to the radius of the wheel times 2 pi. And that's also true for any smaller angle. So I'll roll it back up, and I will rotate the wheel through half of a turn. So if you watch my fingers, my finger moves half of the distance that it did before, or this is pi times the radius, or half of the circumference. So the distance that the string moves is equal to the radius of the wheel times the angle through which the wheel rotates. So a rotation through a fourth of an angle means that my fingers move a fourth of the circumference. A rotation through half of an angle means that my fingers at the bottom of the string move half of the circumference. And a full rotation of the wheel means that my fingers on the string have moved a full circumference of the wheel. So as far as the distance that the string moves, it's also equal to the radius of the wheel times the angle through which the wheel moves. Same thing for the velocity. The velocity with which my fingers move is related to the angular velocity of the wheel, and the acceleration with which the string moves is equal to the angular acceleration of the wheel. So these same equations hold. Distance is equal to radius times the change in angle. So in this case it would be the distance that the string moves. Velocity is equal to the radius of the wheel times the angular velocity, and in this case it would be the velocity of the string. And tangential acceleration, or the acceleration of the string, would be equal to the radius times the angular acceleration of the string. To illustrate that, let me give you an example. An elevator cable winds on a drum of radius 90 centimeters that is connected to a motor. If the elevator is moving down at 0.5 meters per second, what is the angular speed of the drum? If the elevator moves down 6 meters, how many revolutions does the drum make? Now remember that this is a rotational kinematic situation, so draw your diagram just as you would a rotational kinematic situation. List all of your knowns and unknowns, and then you can bring in the extra information that you have relating angular motion to linear motion. So I'll give you some time to prepare that. Okay, well, let's draw our diagrams. Here's our elevator drum initially and finally, and we have the elevator hanging off of it. The elevator moves down. And for convenience sake, so that we're dealing with positive numbers, I'm going to draw my y-axis down. we know that y initial, well, we can call y initial equal to 0, y final equal to 6 meters. The elevator's moved 6 meters down. Vy initial, we're told, is 0.5 meters per second. Vy final, we can infer that it's also 0.5 meters per second because we're told that the elevator is moving down at 0.5 meters per second, and we're not told anything about acceleration or changes in velocity, so we have to infer that Vy final is the same as Vy initial, that it's moving at a constant speed. So that is also 0.5 meters per second. Now we have to talk about the rotation of the drum. We have T initial, theta initial, omega initial, and T final, theta final, omega final. T initial we can call 0. Theta initial we can also call 0. We can start the rotation anywhere we want. And omega initial we don't know. That's one thing we're being asked for. Omega final we don't know. T final we don't know. And theta final we don't know. Theta final is one of the other things that we're being asked for. So, to answer the question that we're being asked, we'll have to include into this our relationships between rotational motion and linear motion. The first question was, how many revolutions does the drum make? Well, that is related to the distance that the elevator travels. Using our equation, distance is equal to radius times the change in angle. That was our first equation. We know that the distance it is equal to 6 meters. Radius, we're told, I forgot to put that in, the radius of the drum is equal to 90 centimeters, which we have to convert to our basic metric units of meters. 1 meter divided by is the same as 100 centimeters. So that makes 90 over 100 or 0.9 meters. So we know radius as well. We were given that. Radius is 0.9. And delta theta is theta final minus theta initial. I'll divide both sides by 0.9. So 6 divided by 0.9 is equal to theta final minus theta initial, which is 0. And that tells us that theta final is equal to 6 divided by 0.9, or 6.66. Theta final is equal to 6.66 radians, which is almost what we're asked for. We know that theta final is 0.66 radians, but we were specifically asked for how many revolutions does the drum make. And so we have to multiply by 1 revolution for every 2 pi radians to get that theta final is equal to 6.66 divided by 2 pi, and that would be 1.06 revolutions, because our radians cancel out. So theta final is 6.66 radians, or 1.06 revolutions. And that was the first thing we were asked for. The second thing was, what is the angular speed of the drum? Well, to answer that, we'll use our other relationship that relates linear velocity to angular velocity, or in other words, V is equal to R times omega. V, we're told, is 0.5 meters per second. The radius is once again 0.9, and times omega. Now, since both the initial and the final velocities are 0.5, that omega could be omega initial or omega final. And so we have omega is 0.5 divided by 0.9. .5 divided by 0.9 equals 0.556 radians per second. And that is both omega final and omega initial. Since we weren't asked for a particular unit for omega, we can use our basic metric units and say that it's rotating at 0.556 radians per second. And that answers the questions that we were asked. There's another type of acceleration that we have to consider, and it comes from the fact that an object moving at constant speed in a circle is accelerating. Think about that. If I ask you, is an object moving at constant speed accelerating? The answer is yes, but why? Well, acceleration, being a vector quantity, has both magnitude and direction, and if we change either one of those, then we have acceleration. So an object moving at constant speed has a constant magnitude, but whenever the direction of the velocity changes, that is acceleration. So acceleration can be change in the speed of an object, change in the direction of an object's motion, or both. So when an object moves at constant speed in a circle, we do have acceleration. Now, the direction of that acceleration might be surprising to you, so I have a demonstration to help you think about that. Here I have a tennis ball on a string, and I will whirl it around and try not to hit anything with it. So I'll get it moving around, moving in a circle. So now I have the tennis ball moving in a circle, and as best I can, it's moving at constant speed. And let's pretend at least that it's moving at constant speed, and also let's ignore gravity. I could also make this ball whirl in a horizontal plane where we wouldn't have to worry about gravity. But I want to show you this so that you can think about the forces on the ball. Let's ignore gravity. Gravity is not part of gravity is a very small part of the motion of this ball right now. Okay, so we have the ball moving at constant speed in a circle. Ask yourself, what's making the ball turn? What's keeping the ball from moving in a straight line? And the answer is the string. The string is exerting the force that keeps the ball from moving in a straight line. If the string were to break, for example, if you imagine, we have to visualize, that's part of the skills in physics. If you imagine the string breaking, what would happen to the ball? It would move off in a straight line because there would be no more forces on it. Well, then gravity would be important. But as far as we can ignore gravity, it would move in a straight line. Now, the force keeping the ball moving in a circle is the string. The string can only pull on the ball. The string is not pushing the ball. So the string is pulling the ball towards the middle of the circle. if we freeze time right here for a second, and you imagine the ball moving upwards, the string is pulling the ball to the left. As the ball gets up to here, we'll freeze time again, the ball is moving to your left, and the string is pulling it down. Over here, the ball is moving down, and the string is pulling the ball to your right. So at all times, the string is pulling the ball towards the center of the circle. So the string pulls the ball always to the center of the circle. That means that the ball is also accelerating towards the center of the circle. That is the direction of the ball's acceleration. So once again, if you imagine, at this point in time, the velocity of the ball is upwards. As the ball moves here, its velocity is now to the left. So what kind of acceleration has happened? Well, its upward velocity has gone to 0, so that means that there must have been a downward force on the ball. And in addition, its velocity has become leftwards, so there must have been a leftward force on the ball. And that is what the string did. The string pulled the ball down and to the left as it moved through this arc. And the ball accelerated down and to the left. The change in the ball's velocity as it goes from here to here is down and to the left. So the lesson to be learned from that is that the acceleration of an object moving in a circle is toward the center of the circle. Think about that for a moment. That's an important thing to realize. It's something that's not intuitively obvious, but it is true. And once you think about it enough, you'll realize that it has to be true. Now let's put some equations to that. The acceleration towards the center of the circle we call radial acceleration. And as we said, when an object moves in a circle at constant speed, it is accelerating. The direction of the acceleration vector is towards the center of the circle, and we'll call this radial acceleration. We have an equation for the magnitude of radial acceleration. The magnitude of radial acceleration is equal to the square of the object's speed divided by the radius of the circle. That is a result that comes from calculus, and in order to derive that relationship, we would have to use calculus, but this being Physics 191, you have to accept that equation as given. So once again, the radial acceleration we can calculate using calculus to be equal to the velocity squared divided by the radius, or if we were to substitute in our relationship between v and omega, we can also write that as radial acceleration is equal to radius times omega squared, our angular velocity. So what that means is that situations with object moving in a circle at constant speed are non-equilibrium equations, meaning that we'll have to bring in Newton's second law for objects moving in a circle at constant speed. Okay, here's a fun example. The rotor is an amusement park ride where people stand against the inside of a cylinder, and once the cylinder is spinning fast enough, the floor drops out. If the coefficient of friction is 0.4 and the cylinder has a radius of 2.5 meters, what is the minimum angular speed of the cylinder so that people don't fall out? You might also have heard of this ride as the gravitron, but basically you're inside a cylinder that looks like the inside of a washing machine tub, and it spins around and the people are held up against the wall without having to stand on the floor. This is a rather complex example. You have to bring in almost everything you've done so far. So I'm going to help you out by drawing a diagram for you to get started. We'll have to draw two diagrams to look at this situation from two different angles. In the first case, we'll look at the gravitron or the rotor from above as it's rotating with some angular velocity. We have a person stuck against the wall. And what I'm going to do is I'm going to draw my x-axis like this, and I'm going to draw my y-axis out of the page. So y is up. Y is coming out of the page at us. We're looking at this from above, so x is to the right and y is coming straight out of the page. Well, what we get from this diagram is we realize that as the person travels in a circle, that person is actually accelerating towards the center of the circle. So the radial acceleration is towards the center of the circle. Now what we'll do is we'll rotate our view and look at this from the side. So here is the wall of the gravitron. Here is the person stuck to the wall, but now this is our x-axis and our y-axis is up the wall. So you can see that whereas we were looking at the gravitron from above, we're looking at a side view now where the wall is here, the person is here, and the center of the circle is in this direction. And the acceleration, the radial acceleration, we know has to be equal to r times omega squared. So now that we know that we're dealing with acceleration, we have to draw in the forces on the person. There are three forces acting on the person. The first being the normal force of the wall. The second being weight, which is equal to mass times g. And the third being the friction force, the static friction force, which is opposing the weight. The static friction force is what's keeping the person from sliding down the wall. And we know that the static friction force is less than or equal to mu static times the normal force. And those are our three forces that are acting on the person. Now, we realize that since the person is accelerating in the x direction, actually in the negative x direction, we have x non-equilibrium and y equilibrium. That tells us that the acceleration in the x direction is equal to the total force in the x direction divided by the mass. And in the y direction, the total force in the y direction is equal to 0. The acceleration is actually in the negative x direction, and it's minus the radial acceleration. The only force that we have in the x direction is the normal force. So that would be minus the normal force divided by the mass. I'll multiply both of these sides by -1 to make those both positive. The radial acceleration is r times omega squared is equal to the normal force divided by the mass. And the radius of the ride we do know. The radius is 2.5 meters. So we have 2.5 times omega squared is equal to the normal force divided by the mass. And that's all we know at this time, so we'll have to go over to our y equation and see that the answer is there in the y equation. Our y equation tells us that the static friction force minus weight is equal to 0, or the static friction force has to be equal to the weight. Or the static friction force is equal to mass times g, or mass times 9.8 meters per second squared. So static friction force is equal to mass times 9.8. Now we know that the static friction force has to be less than or equal to the coefficient of static friction times the normal force. Since we know that the friction force is equal to mass times 9.8, we can write over here mass times 9.8 is less than or equal to the coefficient of static friction, which is 0.4 times the normal force. And that tells us that the normal force has to be greater than or equal to mass times 9.8 divided by 0.4. Now, over here we need the normal force divided by the mass, so we'll divide both sides of this by the mass. Normal force divided by mass is equal to mass divided by mass times 9.8 over 0.4. So we know, greater than or equal to, so we know that normal force divided by the mass has to be greater than or equal to 9.8 divided by 0.4, since mass cancels out. Or the normal force has to be greater than or equal to 24.5. Now, since omega squared is equal to the normal force divided by the mass, and normal force divided by mass has to be greater than or equal to 24.5, we can write that 2.5 times omega squared has to be greater than or equal to 24.5. We'll divide through by 2.5. Omega squared has to be greater than or equal to 24.5 divided by 2.5, or 9.8. And then when we take the square root, we see that omega has to be greater than or equal to the square root of 9.8. Or 3.13 radians per second. So, the answer to the question that we were asked, what is the minimum angular speed of the cylinder? The answer is that the angular speed of the cylinder has to be greater than 3.13 radians per second, or the people will not have enough friction force to be held up against the wall. And the friction force won't be great enough because the normal force is too small. Next time, I'll give you an example of this type to work out. Until then, think physics.